I'm going to get started a little bit early, just because it's so late. I apologize. The people that were here working on the house took forever. So anyway, I want to go over homework 4. Tomorrow in class, I'm going to go over some more problems. And anyway, hopefully we'll all be good for the exam. So the first problem, we need to, using this function, which is actually a function of x and a function of y. We need to find the speed, and then we need to find the speed at 3 seconds, and then we need to find the direction, and then we need to find its direction at 3 seconds, which is, so going over this really fast just to start. So we have the following function. X is 1, t cubed minus 2t squared, and the y part of this function is 1/2 t squared minus 2t, and this will be in the y hat direction. This one will be in the x hat direction. And the first thing we want to find is what is the speed at 0, and then what is the speed at 3 seconds. Now, in order to find the speed, we need to find the velocity magnitude. And in order to find the velocity magnitude, what we need to do is find the velocity. Vx is the x portion derivative with respect to time, and the y part is the y part with respect to time. And then what we're going to do is find Vx squared plus Vy squared. That will give us our speed. They ask for speed, so we don't care about plus or minus directions. Therefore, the time derivative, to take the time derivative of a simple power, you pull down the power in front and subtract 1. So this would be 3 times 1/2 t squared minus 2 times 2t times 2, so 4t, and that will be in the x hat direction. And then for y, we would pull down a 2, so we get 2 over 2. So we just get t minus 2, the derivative of 2t is 2. And if we are going to put in v when t is equal to 0, in the x direction, we get 0 squared minus 0, and then we get 0 minus 2. So we get 0 x hat minus 2 y hat. In order to find the speed, we simply plug these in, and what we get is 0 squared plus 2 with a negative sign squared, which is just 4, but that would end up being 2. So our answer should be 2. And actually, let me actually do this following. I'm going to go the other way with this so that I can make sure I'm not doing something wrong. Hi, Ruben. Hi, Marianne. I just started. I started a little bit early. And I'll go back over what I've done so far. But I want to make sure that I don't mess anything up. So this first question, we were given the following function as x and y. This is really our rx and our ry. In order to find the speed, we need to take the derivative of x and the derivative of y, and that becomes our v. Our v is vx plus vy in the obvious x hat, y hat direction. Taking those derivatives, we get 3/2 t to the t squared minus 2 times 2t. 2 over 2 is 1 times t minus 2. And when we plug in t as 0, our velocity is 0 x hat minus 2 y hat. To find the magnitude, we find bx squared plus by squared and take the square root absolute value, which isn't necessary because it's going to end up being positive anyway. And we get 2. So our speed when t is 0 is 2. Now, our v function, again, was 3/2 t squared minus 4t in the x and t minus 2 in the y. And our second problem is, what is v, or the speed, when t is 3? So plugging in t is equal to 3 in this, we're going to find vx and we're going to find vy. T is 3, so this is 3/2 times 3 squared minus 4 times 3 in the x hat, and vy is 3 minus 2 in the y hat. This would be 9 27/2 minus 12, which is 24/2. So 27/2 minus 24/2, which is 3/2. And vy is just 1. So this is 3/2 x hat, or 1.5. This is 1y. To find the magnitude of v, again, we square vx and we square vy and we add them together and get the square root. So 3/2 squared plus 1 squared is 1. Is 3.25, and take the square root, and I get 1.8 meters per second, obviously. Remember that technically, since they gave us 3.0 as 2 sig figs, even though these are not 2 sig figs, the only thing that we care about is that t was 2 sig figs, so our answer should really have 2 sig figs. So I went with 1.8. My calculator gave me 1.8027756, blah, 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 blah. But really, I only want 2 sig figs. Now, for the third part of this, we want to know what is the direction of the motion as an angle. So what we want to know is, in what direction is it going at t is equal to 0, measured from the x-axis, and then again from when t is equal to 3. So what we need to do is figure out, essentially, what we need is we need to find our displacement vector, which was, again, if we go to the top, our displacement vector was 1/3 or 1/2 cubed minus 2t squared in the x plus 1/2 t squared minus 2t, 2 squared minus 2t in the y hat. So we want to know what is the direction of this vector with respect to the x-axis. But if we plug in t is equal to 0, this all becomes 0, this all becomes 0, and what we should have is 0. Now, are they actually considering that to be the velocity? So what they want is they want the direction of the velocity. All right, so I'm dumb. It wasn't clear. So they meant they want the direction of the velocity. And remember, the velocity when t was equal to 0 was 0 in the x hat and minus 2 in the y hat. Now, without doing anything, if you just draw the vector, this is the vector that is 0, minus 2. It's the vector from the origin to the point 0, minus 2. And you can see that that vector is at 270 degrees or minus 90. I believe it will take either one, so 270 degrees or minus 90. Now, when we found the velocity when t was equal to 3, what we got was 3/2 x hat plus 1 y hat. And that means our vector looks something like this. go over 3/2 in the x, go up 1 in the y, and your vector will be along the diagonal of the rectangle formed by that. However, mathematically, you would take the arctan of y over x, and that will give us the arctan of 2/3 is 33.7 degrees. They're taking only 2 sig figs, so they get 34. So the main thing I wanted you to make sure you could do is a simple derivative and then plug in t to find the instantaneous velocity at t is equal to 3. And then make you remember how to find an angle from the x-axis using components y and x. I think that's pretty simple. I probably made it harder than it was. And the problem wasn't super clear in the last two parts that it wanted the velocity, not the position vector. It just said the motion. So just know that they want the velocity angle. All right. If you have questions, just go ahead and jump in the chat. The next question is a velocity addition. This will not be on the exam, but it is in the homework, and I want to make sure you know how to do it. So first, let's draw this. A kayaker wants to paddle across a 100-meter wide harbor. The tide is going out, creating a tidal current that flows to the east at 2 meters per second, and the kayaker can paddle at a speed of 3 meters per second. But we want them to travel in a straight line. So we have the following. We're going to assume that they are going to go north, and they need to go 100 meters. That's where they want to get to. However, this is outward. There is a velocity outward of 2.0 meters per second. And we want to know in what direction should they travel to travel in a straight line. Now, what this means is doing our velocity way. We want the velocity of the kayaker versus the ground. This is the distance along the ground, which should equal the velocity of the kayaker to the water plus the velocity of the water versus the ground. Now we need that in x and y, and in x and in y. And this is kind of a overly complicated way to do this, but it works. Kayaker versus the water in the x hat plus water versus the ground in the y hat, and kayaker versus the water in the, in the x hat, plus water versus the ground in the y hat. Now, we did this one in class. The velocity of the water versus the ground is actually going to be positive 2.0 meters per second in the x hat direction. East is x. The velocity of the water versus the ground in the y is 0. Okay, so we know already that this is 2 meters per second, and this one is 0 meters per second. Then what we need is the kayaker can go 3 meters per second at most. However, the following is true. We don't want the kayaker to have any velocity in the x direction. So we're going to put a 0 in the x direction. And what that means is the kayaker's water velocity plus the kayaker's or the water's velocity should equal 0. That's pretty easy to see that the following must happen. The kayaker, the velocity of the kayaker over the water must equal the negative 2 meters per second. Now, in order for that to happen, the kayaker speed versus the water we know is going to be 3 cosine of theta. So negative 2 has to equal 3 cosine of theta. The reason for that is this part of, if this is the velocity of the kayaker versus the water, this is the velocity of the kayaker versus the water in the x hat. This is the velocity of the kayaker versus the water in the y. This vector has to cancel this vector. And that is going to tell us the angle, and it's going to tell us how fast he can move across the water. So to do that a little bit more succinctly, what he has to do is he wants to go straight across in the y direction, 100 meters. But the current is trying to make him go 2 meters per second to the right. So he's got to travel at some velocity to the left such that the velocity in x cancels out the 2 meters per second. So his x velocity, v total in x, be 0, and that's going to equal the velocity of the kayaker plus 2 meters per second, or the velocity of the kayaker needs to be, in the x direction, needs to be 2 meters per second. However, this is v cosine of some angle here, or some angle here. We'll figure out what that is. I actually want to use this one. So this is doing it without all the velocity addition stuff. Now let's see what they're actually going to ask us to do. In what direction should he paddle? Now we know that v is 3 meters per second. That's how fast he can paddle. And therefore, v cosine of phi is equal to negative 2 meters per second. Therefore, phi is arc cosine of negative 2 over 3. If you don't know how I did that, this is cosine of phi. This is negative 2. Divide through by 3. Take the arc cosine on each side. The arc cosine of negative 2/3 is 132 degrees. You don't have to add 180 here. Cosine will give you the right values. So that looks about right from here. This is 90, so it's a little bit more than 90. It's not quite 180. So that should be correct. Next, how long will it take them to cross? Okay, so this is a little bit harder. We now know that their velocity in the x is going to be 0. However, the total velocity is equal to the square root of the velocity in x plus the velocity in y. We know the velocity in x will be negative 2. Square everything, and this becomes v magnitude squared is equal to vx squared plus vy squared. We're on the second problem. We know that this is our negative 2. We know this is 3. So vy squared is v squared minus vx squared. Just subtract that. Turn this into a square root. And what we get is we get 3 squared minus 2 squared, which is 9 minus 4, which is square root of 5 meters per second. That is the velocity in the y, but that's the only velocity because the velocity cancels in the x. So what we have left to do is we know that he's got to cross 1,000 or 100 meters, and his velocity is constant, root 5 meters per second, and we want to find the time. So x final minus x initial is v times t, or t is x final minus x initial over v. X final will be 100, x initial will be 0, so this will be 100 divided by square root of 5 meters per second, which will give you seconds. So 100 divided by square root of 5 is 44.7 seconds. which is 45 seconds if you round to 2 superfluous, which is fine, even though our answer really should probably only be 1. 45 seconds is about how long it will take them to cross. Hopefully that all made sense to you. This is a very hard problem. The main thing to remember is that you need to realize that the river is moving this way at 2 meters per second. So he needs to move in the X direction to counter that. And then whatever is left over will be his Y. And this will be the amount that he could move at. Therefore, we know that this has to be -2 so that he only moves north. And then if that is -2, then v squared is equal to vx squared plus vy squared. You can use that to find vy. Once you have vy, take the distance over vy, and that gives you the time. And that's all you have to do. Hopefully that all made sense. Anyway, it's a little bit of a pain of a problem, but hopefully it's not too bad. The following problem maybe, look, because there's 2 different kinds. Yeah, this is angular velocity, and we'll talk about that in a second. But we want the angular velocity and we want the period. Now remember that the angular velocity omega is, because s is the arc length, if we rotate through some angle, s is our arc length, r is our radius, and that's our angle, so s is r theta. We take the derivative of this, we get v is r omega. And if we take the derivative of that again, we get a is our alpha. S is the distance you rotate through, like the distance around. If you went all the way around, S would be 2 pi r, which is the circumference. V is the velocity along that path. And then the acceleration is how V is changing. However, because different radii or objects at different radiuses would have different V's, what they actually have in common is they all rotate through the same angle, and omega is the angular velocity. It's how their angle changes with time. They all, no matter where you are on the disk, you have the same omega, and you have the same alpha. Alpha is how omega changes, omega is how the angle changes. So what they're asking us to find is omega. They've given us, however, 45 RPMs. And 45 RPM, RPM means revolutions per minute. We want to turn this into radians per second, okay? Now, first of all, there are in 1 minute, 60 seconds, so going all the way back to the first week. And in 1 revolution, there are 2 pi rad in 1 revolution. So if we multiply this by 2 pi over 60, we turn this into rads per second. That's the first thing we want. So omega is 5 times 2 times pi divided by 60, which is 4.71. Okay, so revolutions per minute, there are 2 pi radians in 1 revolution. One trip all the way around is 2 pi radians. And in 1 minute, there are 60 seconds, so you just convert it. So we got 4.71 rads per second. Now the period, this is actually kind of nice. The period, if you remember, was 2 pi r over v for uniform circular motion. However, looking at this, v over r is omega. Just divide by r on both sides. Therefore, this is equal to 2 pi over omega. The period is 2 pi over omega, and that's very nice. The units would be 2 pi rad over rads per second. to give you seconds. So all we have to do is divide 2 pi by r omega. 2 times pi divided by 4.71 is about 1.33 seconds. It is a very nice relationship to remember. 1.33 seconds. And that's it. So what to remember from here? RPM is converted by 2 pi rad per revolution and 1 minute over 60 seconds. That can PM to omega. And then T, which is 2 pi R over V, is also 2 pi over omega, since omega is V over R. Hopefully that makes sense to you guys. So that's it. It's not too hard of a problem. It's just a little weird. It's stuff that we didn't specifically talk about in class, but I figured you guys could figure it out. All right. This is centripetal acceleration. And if you remember, for centripetal acceleration, we assume that this thing's going around in uniform circular motion, which means B is constant, although the angle changes. A, centripetal, is B squared over R, but it's in the direction of the center of the circle. So this is our AC, and B is however fast we move. The only other thing we have here is 2 pi R over V is our period. And that means that if we solve this for B, we get 2 pi R over T, square everything and plug it in here, and you get 4 pi squared, R squared over R is just R over T squared. So you can equate those if you need to for some reason. In our problem, a peregrine falcon makes a tight turn, and in that tight turn, it can have a centripetal acceleration of 1.5 times free fall acceleration. That means 1.5 times g, or 1.5 times 9.8. What is the radius of the turn if the falcon is flying at 17 meters per second? So I know that AC is going to equal 1.5 times the free fall acceleration. Don't worry about the negative sign. Yes, we know it's inward, but we don't worry about that. Our E, we're told, or at least I was told, you probably have something different, is 17 meters per second. And we want to know the radius. So using this, solving for R, multiply through by R, divide through by AC. R is B squared over AC, which is 17 divided 17 squared, so divided by 14.7, or 19.7 meters. 20 meters. They want 2 sigmas. And that's it. 19.7 meters. These problems are super easy and super nice because they're easy. They're plug and chug. You will have something somewhat similar to this, probably a little harder on the exam. In the early questions that are pretty fast, plug numbers into the correct equation. This was a nice exam problem. Anyway, make sure you know how to do it. All right. A supply plane needs to drop food to people on a glacier. This is a projectile motion problem. And when we do projectile motion problems, the first thing that we remember is that we have to usually decompose B into V naught of X and V naught of Y. This sometimes happens. In this particular problem, we're not going to have to, but just remember. Our next step is draw a picture, make sure you don't have to decompose it. And then we're going to list our variables in the following way. V naught of X is Vx. V naught Y, V final Y, A of Y, t, and a of x. A of x is 0, which tells us that these are the equations, and b final of x is b initial of x is b of x. For the y equations, they're free fall. So they are y final minus y is b naught y minus gt squared over 2. B final y is b initial y minus gt. B final y squared minus b initial y squared is minus 2g. And finally, if you want to use it, although I never do, b final y plus b initial y over 2 times 2. And normally what we'll have to do is we'll have to find the time and plug it back into x, or we'll have to find the time and plug it into y, one way or the other. We can make these two things match. And that's because the time at any moment should be the same in x and y. Anyway, let's now look at our problem in a little bit more detail, and then we'll come back to this page and work from here. Now our problem is we got to drop a supply package, and the plane is flying 150 meters above the ground at a speed of 160 meters, okay? So what that means is our plane is flying at 160 meters per second, horizontally, at a height of 150 meters. Now let's start labeling a few things. This is our V naught of X, and our V naught of Y is 0 because the package isn't falling yet and it's not going up. So the package has the same speed as the plane when it's released. This will be our Y initial. This will be our Y final, which will be the ground, obviously. We always have to measure Y up because we're going to assume that AY is negative G. If we assume that this was 0 and the ground was 150, we would drop the negative sign in front of all the G's. We're not going to do that. But once you get more sophisticated with this, totally legitimate to do it. For now, I want you to do it this way. What we want to find is where we start is our 0. We want to find what X final is, because this distance, X final minus X initial, is what we're trying to determine, because that's how far in front of the supply drop we want to unload this supplies so that they come down and hit there. So we're going to try and find X final minus X initial with the following variables. Let's go back a page. Y initial was 150. Y final was 0. V initial was 0. A, Y was minus G, meters per second squared. T was unknown. V final Y was unknown. We don't know either one of those things. Then X initial was 0. X final is unknown, but that's what we want to find. This is what we're trying to find. V initial of X was 160 meters per second. This was unknown. This was 0. So in order to find this, we need Vx and we need T. Therefore, we can't find T from the X equations because we don't know X final. So we have to find T from the Y equations and then substitute it into the X equation to find what X final is. Now, going back to how we did free fall, we have two unknowns. We want it solved for time. We don't care about V final. So we go to the equation that does have V final. And the only one that fits that case is this. What we're going to do is we're going to solve this for T. We're going to plug it in here. Now, Y final minus Y initial, V naught of Y, T minus GT squared over 2. We know Y final is 0. We know Y initial is 150. We know V naught is 0. And we're going to find T. So what we have is we have minus Y naught minus G to the half T squared. multiply by a 2 over g with a negative sign on both sides, and you get t squared is 2y0 over g square root. You're going to take the positive sign. The negative signs cancel. Y0 is 150. G is 9.8. So 2 times 150 divided by 9.8, and then take the square root of that, and I get 5.532, don't round yet, seconds. Now, I want to find x final, and I know this is true, and x initial, or b of x was 160. This is 0. I really just want to find x final. So this is 160 times my 5.5328. So times 160, and I get 885 meters. Let's double check myself, 885. And that was the only thing you needed to answer. So what we did here, you had to draw it correctly. And you had to understand that if the plane's moving this way and you just drop something out, that package is going to have an initial velocity in y of 0 and an initial velocity in x of 160, or whatever the plane's flying. Your initial height, 150, the final height that's the ground is 0. And then understanding that we need to find x final. That's really what the question was asking us. So when we look to here, in order to find x final, we need time. We know vx, we don't know time. The only way we can find time, because we can't find it with the x equations, is using the y equations. And then this was just the way we did free fall again, which is why we did free fall to start with the way we did it. Write your variables, look at them, see if you know enough to solve for whatever you're looking for. In this case, we're looking for time. We didn't know v final, but we didn't need v final to find time. This is pretty much what I'm going to ask you to do on an exam question. I'm going to ask you for some concepts or equations. One concept, the acceleration in the x direction is 0. The acceleration in the y direction is we always have to go positive y upward. The following 6 equations that you have there, those are all great things that you can write down. You only need to write down 3 or 4 or 5 of them. The point being that I want you to get your tools together, your tools being your concepts and your equations, before you start doing the problem. You never know what you might need. Alternatively, at the end of the question, you can come back and just write whatever equations you use there, and that's totally fine too. The next step would be to write down your variables for whatever specific part of the problem you're solving for. You might have multiple parts to a problem, so draw it, write down your variables, figure out what equations you need to solve for whatever you're being asked to find, and then do the algebra and solve them. Projectile motion is a little harder than free fall because we have 2 sets of equations in effect. And you're usually substituting one into the other to solve something. Anyway, I hope you all get that. We'll do more of these in class. Shot put. Athlete throws a shot with initial speed at an initial angle and at a height that is not 0. So what I'm going to do is I am going to actually cheat a little here to erase all of this stuff, and we will reuse this for this following problem. So let's kind of draw a picture here. Shot putter throws a shot at an initial velocity of 12.8. This is your V naught at a 40-degree angle. And they are actually 1.8 meters above the ground when it leaves the air. The shot leaves at a height. Now, how far does it travel? So what we want to know is how far does it go before it hits the ground at y is equal to 0, y final. Our y initial is 1.8. Our x initial is 0. And our x is, but that's what we want to solve for. Okay. First step, we need to find, I don't know which is, I don't know what that just did. We need to find B naught of X and B naught of Y. B naught of X is B naught cosine of our angle, and B naught of Y is B naught sine of our angle. So this is our B naught of Y. This would be our B naught of X. But 12.8 cosine of 40 and 12.8 sine of 40. That's usually your first step that you really want to do if you have an angle and B naught to worry about. This is 9.80536. You can go as far as you want. I recommend going 3 or 4. 12.8 sine of 40 is 8.27, 8.22768. We don't want to not go enough, because if we round too soon, sometimes we'll get the wrong answer. We need to again find X final. Just like before, we don't know the time. So we're going to find the time, and then we're going to find how far it went. X initial was 0, Y initial was 1.8. X final is unknown, but that's what we want. B initial of X was 9.80536. And T is unknown. Again, A of X is 0, Y final is 0, it hits the ground. V initial of Y is 8.22768. 22768. V final is unknown, and T is unknown. So we need to find T, and we don't know V final. Now, you might be thinking, I'm going to have to do a quadratic because I have B naught of Y here, that this is the one that doesn't have any V final. However, let's do something different. V final squared minus V initial squared in the Y is equal to minus 2G Y final minus Y initial. And V final is B naught GT. Now, if I rewrite this, I get the square root, positive or negative, and it's going to turn out to be negative. We'll talk about that. B naught of Y squared minus 2G Y final minus Y initial. Looking at our variables, this is going to be negative because it's going to be going down at that point. But this is our 8.22768 squared minus 2 times 9.8. Y final is 0 minus 1.8. And that is going to give me 8.22768 times 8.22768 minus, but not minus because the minus sign cancel, 2 times 9.8 times 1.8. Square root of that answer is 10.147 meters per second, but that's negative. Using this equation to find time, I get that time is B final Y minus B initial of Y over minus G. This is negative 10.147. This is positive 8.22768. So these are both going to be negative, and we're going to divide by negative 9.8. So 10.147 plus 8.22768 divided by 9.8, and I get 1.875. So T is 1.875 seconds. In order to find X final, all I need to do is multiply Vx times T. So take that 1.875 and multiply it by 9.80536, and I get 18.4 meters. So X final is V of X times T, B of x is 9.80536 times this, 18.4 meters. Now, you might want to take a picture of this and grab it. One thing you might notice, if you look at the YouTube too early, it'll actually get clearer as we go, okay? So if you look at it tomorrow after it's uploaded fully, you'll be able to read this. If you try and look at this like while it's loading, at first it's going to be all blurry and hard to read. However, this is a very nice way to look at this. Now, the other way we could have done this, had we wanted to, is we totally could have solved the quadratic. And the quadratic was y final minus y initial is v naught y t. Now again, a quadratic has to be of the form ax bx plus c. And then you take minus b plus or minus b squared minus 4ac over 2a. RA here is the, if we reset this to 0, we get negative g to the half times our squared variable plus b naught of y times our single variable. And if we move this over, it becomes negative y final minus y initial. The negative sign means this is plus y initial minus y final. So take a negative sign times that. So A is negative g over 2. B is b naught of y, and C is y initial minus y final. Our y initial was 1.8. Sorry, let me actually do it symbols. Our y final is the ground. Our b initial of y was 8.22768 meters per second, and this is minus 9.8 divided by 2. Plugging these things in, I get negative 8.22768 plus or minus 8.22768 squared minus 4 times minus g over 2 times 1.8. All of this over 2 times minus g over 2. Now, plugging in numbers under that square root, 8.22768 times 8.22768. The minus signs cancel, so plus 4 times g to the half, which is 2 times 9.8 times 1.8. Square root of this answer, 10.147. So I get negative 8.22768 plus or minus 10.147. It's called 10.148. Probably shouldn't be rounding that much, over negative 9.8. If I take negative 8.22 plus 10, then I'm going to get a positive number divided by a negative number, and this has to be time, so I can't do that. I need to get a positive time, which means I'm going to take negative 8.22768 minus 10.1476 divided by negative 9.8 to get a positive time. So add 8.22768 divided by 9.8, and I get 1.875 seconds, which I believe is what we got, 1.875. You can do it either way. If you like quadratics, if quadratics don't bug you, but basically anytime y initial and y final are not the same, they're not both 0 or they're not both the same, you're going to always end up having to do a quadratic to get time. But you could also find b final, which doesn't involve doing a quadratic. To find b final, you just have to solve this equation for b final, and then use b final in this equation to get time. It's really up to you. Neither are more correct. I tend to mess up my quadratics, so I don't do quadratics in real life. When I'm teaching, obviously. All right, we did this one in class as well. A kangaroo jumps 10 meters from its takeoff point at a 25-degree angle. So this kangaroo jumps 10 meters. That 10 meters is its x final. And the only thing we know is that it jumps from a 25-degree angle. We don't know what V naught is, but we want to find it. All right. Let's just do some of our variables to begin. T, V of x, y initial, y final, V initial of y, V final of y, A of y, T, A of x. Now, x initial was 0. We start from 0. X final is 10. We don't know what t is. V initial of x, or v of x, is just v naught cos theta. V initial of y is v naught sine theta. And we don't know what those are yet. We don't need to know quite yet. We don't know what this is. We don't know what this is. But we do know that y initial and y final are both 0. That is helpful. What we're going to do is, as always, we have x final minus x initial, vx of t. And if we substitute in symbolically, we get v naught cos theta of t. And this is what we want. They're asking us to find our v naught. We know x final is 10. We know x initial is 0. We know this is cosine of 25. We don't know t and we don't know v naught. So we need to find t from our y equations. And we don't know v final. So that tells us we go straight to this one, the only y equation without. Further, because v initial is that, further, because y initial and y final are both 0, this is super easy. 0 is v naught y, t minus gt squared over 2. Move that over, solve this thing for t. T is equal to the square root of 2 over g. Move that over, you get gt squared over 2, divide by t, multiply through by 2 over g. V naught cosine, V naught sine. Let me actually go back for a second. Rewrite this for you. So I get g t squared over 2 is v naught sine theta of t. Now, if I reset this to solve for t, I get g t over 2, or I mean to solve for v naught sine theta. I don't know t. The other equation that I had was x final minus x initial is v naught cosine theta of t, or times t. And from those two, I'm trying to find v naught. I don't know t though. I know everything else in this. If I solve this for t, t is 2 over g v naught sine theta, and plug it in here. I get x final minus x initial is v naught times cosine theta times 2 over g times v naught sine theta. And the following is true. Don't do that, James. 2 cos theta sine theta is equal to sine of 2 theta. It's a trig identity. You just have to know it. So this becomes x final minus x initial is this, and this become sine of 2 theta. I'm going to divide by g, and then I'm going to have v naught squared. And v naught's what I want. So v naught squared is x final minus x initial times g divided by sine of 2 theta. Remember, this was squared, so we're going to take the square root. X final was 10. X initial was 0, so 10 times 9.8 over sine. Theta was 25 for me. Sine of 50. 10 times 9.8 divided by sine of 50 degrees. Taking the square root, I get 11.3. My v naught is 11.3 meters per second, or 11. 11. They want just that. This is about as hard as it gets when y initial and y final. It's always a pain to find the initial, to be honest with you. And finding the angle itself, if you don't know the angle, I will never ask it on an exam because you can get in a lot of trouble. It can just go, you guys, if you haven't done enough of these problems, it can end up really messing you up and wasting a lot of your time. And that doesn't show me that you know how to do a projectile motion problem. That just shows me that you haven't quite done enough. So this is about as hard as it gets for projectile motion, to be honest. You have to know that you're going to solve the x equation and the y equation, and then substitute in one of them for t. Anyway, this one, this linear trend line, notice this is omega versus t squared. I don't know why I'm being so worried about this again. For a normal equation, linear equation, this is y, this is x, and you have some line that is mx plus b. This trend line is y is mx plus b. B is where it intercepts when x is 0. So if x were 0, it's whatever y equals. M is the slope of this line. Okay. So our function, which is along the y, is omega. Our trend line is omega is 42. I'm going to come back to that, plus 32. But this is 42x. Our x is t squared, and that's totally legit. You can do t squared. You can always linearize a function. So that gives you a slope. In this case, though, they want to know what is, when t is equal to 0, what is our angular velocity omega? Well, if you look at the trend line, that's just the intercept, 32. Plug in 0 for t, so x is t squared. 42 times t squared is 0, plus 32, you get 32. You can see it either way. Next, they want to know the angular acceleration at t is equal to 2 seconds. But remember, this is our omega. So alpha is just the time derivative of omega. The time derivative of this is 42 2t plus 0. There's no derivative of this. There's no time on that. Now, 42 times 2 times t, when t is equal to 2, 2 times 2 is 4, 42 times 4 is 168 or 170, which is what they got. I would say it's 168, which is fine. But you just take the time derivative of the trend line to get your alpha, because it is that. And then finally, how many revolutions does it make between 0 and 2 seconds? In order to find the change of theta, the change of theta is the integral with respect to time of our trend line. Time 1, time 2. We have one more thing to do, but so this would be 42 t squared plus 32. Integral from t is 0 to 2 seconds. The integral of omega dt is the change of angle. The integral of alpha dt would give you omega. Therefore, the derivative of omega is alpha, the derivative of theta is omega. Anyway, doing this integral is pretty easy. Raise the power, divide by the new power. I get 42t cubed over 3. There's no power there, so it gets a power. And then you take the limits from 0 to 2. Happily, we don't have to worry about 0. So what we get is we get 42 thirds times 2 cubed plus 32. This is 8 thirds. 42 times 8 divided by 3 plus 64. I get 176. So this integral is equal to 176 rad. But that's not what they asked us. What they asked us was, how many revolutions does it make? Now there are 2 pi radians per revolution, which means we're going to add this by 2 pi rad per revolution to find the number of revolutions. And that gives us 28, which is the answer they got. So again, the intercept is omega when time is 0. The derivative of the function is your alpha. And because that is an instantaneous alpha, you're going to want to plug in a time on that derivative. And then the integral of that trend line with respect to time gives you the change of angle. And because it's an integral, you have limits between those limits, but there are 2 pi rad per revolution. It's kind of a tough problem, but it's not that tough if you know how to do integrals. Anyway, this final one is a angular acceleration problem. Angular acceleration is not constant in the problem. However, these are exactly like any of our constant accelerations. I'm sorry, the acceleration is constant. So this would be v initial t plus a t squared normally. What we get is theta becomes our x, but you need to remember that theta by itself has to be in radians. It can't be in degrees. This is just all of the constant acceleration equations with a replaced by alpha. Alpha takes over for a, omega takes over for v, theta takes over for t, and theta needs to be in radians. Otherwise, you've got problems. Last one that we probably need. And what's nice is you're not going to be doing any substitution stuff. It's straight up like free fall. Now, negative alpha means it's slowing down. Omega is 0 at rest or at stop. So if it comes to a stop, omega final will be 0. If it starts at rest, omega initial will be 0. A computer hard disk, 8 centimeters in diameter, is initially at rest. There's a small dot on the edge of the disk. It accelerates for half of a second at 580 radians, and then it coasts for another half. What is the speed at the end? We have 2 particular times. This is when alpha is 580 rad per second squared, and this is from t is equal to 0 to 0.5. Then alpha is 0 from t is equal to 0.5 to 1.0 seconds. Omega is constant, and we don't know what it is. Omega initial is 0 starting from, and we want to find omega final. Okay. We're eventually going to the speed of the, now, we'll talk about that in a second. But whatever speed we find here will be the speed for here. For the second half of the time, it just stays at whatever constant omega. Now, omega final is omega initial plus alpha t. This is 0, alpha is 580, t is 0.5. Half of this is 250, 290. And we did do this in class. However, we want v, and v is equal to r omega. Now here's the problem. If you read this, R is half the diameter. So R is the diameter to the half, but it also needs to be in meters. Centimeters is 0.08 divided by 2, 0.08 meters. So this is 0.04 times 290 rad per second meters. You'll notice that velocity of meter give us meter per second times rads. Rads are not units. They are just a way to delineate rotation. I get 11.6 meters per second for B, which is 12. And notice that because it's constant, this is going to still be 290 rad per second or 12 meters per second. For the whole final half second, it's going to stay the same because it basically spins up half second to 290 rads per second or 12 meters per second, and it just rotates at that speed. This is a little bit harder to realize. Talking about the dot is on the edge. The edge is at a radius of half the diameter. Okay, so do not mess that up. Then we want to find how many revolutions. Now, again, what we have to do is we have to find theta final minus theta initial for the first part and theta final minus theta initial for the second part. What I'm actually going to do is call this theta 1 minus theta initial and then theta 2 minus theta 1. When we have constant, omega final is omega because it's constant. And therefore, theta final minus theta initial is omega t, whatever this final from part 1 is. And this will be whatever our theta from part 1 is. So in order to find how far it went, we're going to find how far it went in the first time and then the second time. Now, we know the time. T is 0.5 seconds for the first part. We know the time for the second part is also 0.5 seconds. Omega initial here was 0. Omega final, we don't know. Actually, we already figured out it was 290 rad per second. And alpha was 580 rad per second squared. So what I'm going to do is omega final squared minus omega initial squared is 2 alpha omega final minus omega initial. This is 0 because it started from rest. And we said that omega final we're going to call omega 1. So omega 1 also started from rest. Omega 1 is omega final squared divided by 2 alpha, or 290 squared over 2 times 580. That was 290 times 290 divided by 2 times 580. I get 72.5 rad. So this is omega final is omega 1 plus omega final times t, which is 72.5 rad plus 290 times our next 0.5, or half of this, which is 145. So 72.5 plus 145, which is 217.5 rad. But we want revolutions. So again, divide by 2 pi rad per rev. And I get 34.6 revolutions, which they're calling 35. All right. These problems are actually super easy because you only have you only have the theta final minus theta initial, omega initial t plus alpha t squared over 2. Omega final is omega initial plus alpha t. And omega final squared minus omega initial squared is 2 alpha. Theta final minus theta initial. And if you really want to use it, theta final minus theta initial is omega final plus omega initial over 2 times 2. And then the only thing you need to remember is negative alpha means slowing down, and rest means omega initial is 0. Coming to a stop means omega final is 0. And thetas in radians, they have to be in radians. You cannot do like 60 minus 30 degrees. This doesn't work if you do that. Okay. But otherwise, it's actually super simple if you do a few of these. They're not too bad. All right. Well, thanks everybody. Again, I am so sorry it was so late. Since we only have 2 more days, I wanted to make sure you had time to do at least the projectile motion ones. This stuff won't be on the exam. We're going to actually do it later when we do rotation. We're going to use it more when we do rotation. So it's good to see it now a little bit. And the very beginning, taking the derivatives, that will be on the exam. So just make sure that you do go over how to take derivatives, and make sure that you understand the projectile motion stuff. This was really easy. This one you do not. Number 2, I'm telling you, will not be on exam. You're not going to have to do something where you add the velocities. However, this is a good problem. Remember, take the derivative of x, take the derivative of y with respect to t, and then the magnitude of b is bx squared plus by squared square rooted. And the angle is arctan of by over bx. So just make sure you know how to do those. Other than that, I will see you guys in, I don't know, what is it, 11 hours? I'll see you guys soon. If you have any questions, let me know. Otherwise, I'll see you tomorrow. Good night. Thanks for coming. Get some sleep, everybody. Bye, guys. Marianne and Joseph, are you okay? I'm going to turn this off. Bye, guys. Hopefully you didn't fall asleep. It will be posted soon.